All right, we're going to take a look at quadratic functions. Now, we're going to look here, from chapter 8, we looked at a polynomial of a degree of 2, such as negative 16x squared plus 64. That's called a quadratic polynomial, but we're going to use it as a quadratic function. And it allows us to make a prediction. So for instance, the cat knocks off a flower pot off the railing. Okay, there is a function that's happening as that flower pot is falling, versus, I guess, if the cat's falling. Let's take a look at this. As an object falls, its speed continues to increase, so the height above the ground decreases at a faster and faster rate as it's picking up speed. We're going to ignore air resistance on this one just so we can have just this constant amount that we're looking for. You can model that height with this function, h equals negative 16t squared plus c, with the height of h, which is changing, and then the time t in seconds, which is changing, and the initial height is c, which is going to be a constant amount. So let's take a look at this. An acorn drops from a tree branch 20 feet above ground, so we can start to see some of the pieces of our equation with this function. So there's where 20's showing up. It gives us the height h of the acorn in feet after t seconds. With the graph, what is the graph of this quadratic function? So, and we want to figure out what time that acorn is going to hit the ground. So we have a negative 16 as our constant rate of change happening here. So the way we do this one is, the first one is kind of take a look at what's going on, and what we need is we need to graph some of the relationships. So we're going to start off with t equals 0. So when time is 0, we know that our height is going to be at 20. So we can plot that point. Then we're going to try it if t is 0.5. So when I put it in my equation, I can see that negative 16 times 0.5 squared plus 20, and I end up with 0.5 squared times negative 16 is negative 4, and I take that plus 20 and I get 16. So 0.516 is going to be like right around here. And then I can try 1 with 1 squared minus 16 plus 20, and I end up with 4. So 1 and 4, so it's just below that line. And then I can try 1.5, so I've got negative 16 times 1.5 squared plus 20. And when I simplify that, I'll end up with negative 16. Now with negative 16, I'm not going to, let's see, 1.5 negative 16, that's going to be somewhere down here, and we're not going to plot that because we don't have a height of negative 16 for this particular situation. So about what time does the acorn hit the ground? It had said right here somewhere, it looks like just below, or just more than 1 second, it looks like. I tried to find this out for sure, where time is 0 and negative 16 t squared plus 20. And so I tried this out. So I subtracted 20 from both sides. If I wanted to be more exact, negative 16t squared divided by negative 16, and I ended up with 1.25 equals t squared, and I square root both sides, and I found out that it actually, square root of 1.25 is right on 1.12, so my estimated answer is just over 1 second, while my actual time is just over 1 second is when this happens. So when you estimate, you can go ahead and just look at your graph. If I'm asking exactly, then you can plug in y equals 0 and simplify that. All right, why don't you try it? We've got an acorn dropping from a tree branch that's 70 feet above the ground. There's my function. Why don't you play this out? Again, you're going to need a t-chart for this one. And try it out. Press pause. So here's the relationship. I tried out the time of 0, 0.5, 1, and 1.5 because I knew the information was going to change really quickly. My height was, and when I played it out, I got 70, 66, 54, and 34. I graphed that out, and again, my estimate, my graph showed me that it's going to be a little bit more than 2 seconds, but I tried it out because I wanted to know kind of for sure if my graph was real, because I was kind of doing a bad sketch over here. So I plugged in y being 0, or my height being 0, and I ran through my equation and found out that the square root of 4.375 is 2.09. So I saw that it's going to hit the ground at just over 2 seconds, like my graph was showing me. Now we use this equation, well, now what happens here is if an object is projected into the air, we are now given velocity. And that does influence everything, and influences not only the equation, but even then my graph. So then we see something happening here. We have a middle term of VT. So during halftime of a basketball game, a slingshot launches t-shirts at the crowd. The t-shirt is launched with an initial upward velocity of 72 feet per second. The t-shirt is caught 35 feet above the court. How long will it take for the t-shirt to reach the maximum height on this one? We're going to look for the maximum height, which is what is the range of the function that models the height of the t-shirt over time. So here's our function right here. Is the height is negative 16t squared plus that 72, which is our change, plus 5. So it must be starting at plus 5. I'm thinking like the guys over have that 5 feet height that it's starting from. Since the coefficient is t squared is negative, the parabola that tells us a couple things. It's going to open downward. It's yeah. So let's see what else happens. The vertex will be that maximum point. So it can tell us a few different things. In problem 2, okay, suppose the t-shirt is launched with initial upward velocity. So I'm changing the velocity. I'm going to change a few different things here. So how long will it take for the t-shirt to reach its maximum height? Let's come back to this last one. Let me pause it a second. I didn't give you the maximum height of this one. So we're trying to find the height of the parabola on this one. So that is the vertex. So we're going to be using our formula. So it's going to be negative b over 2a. And that's going to be one of my coordinates of my variables. So negative my b term. So here she is 72 over double my a term, which is negative 16. So I got my negative 72 over double my negative 16, and I get 2.25. Okay, so that's one of my terms. So now I'm going to go ahead and plug it in for my height, because I know my time. So I have negative 16 times 2.25 squared plus my 72 times my 2.25, and then I have to include the height of the guys there. And when I simplify all that, I see that my height is at 86. That's when my parabola turns. So it's being launched, and that's the point where it is at its highest point at 86 feet. Now I want you to try that out. Again, continue to use your ratio. Find your x term to solve for your y term. Press pause. When I used my ratio, I found my x term of my vertex being 2. I plugged it in, and I found my y term of being 69. So at the point 269 is where my vertex is. So I can see my height is going to be greater than or equal to 5 feet, and it's going to increase all the way up to 69. All right. Instead of going to launch t-shirts, I'm going to go launch some gerbils and then run and catch them, because that would be the nice thing to do.